Good morning and good evening everyone, and welcome to this tutorial on Apache Spark, and where we will learn about Apache Spark, features of Apache Spark, its architecture, Spark's ecosystem, Spark components. We'll also discuss a case study, and then we will have a Spark demo. Now, what is Apache Spark? So all of you might be already aware that Spark is gaining a lot of popularity due to its in-memory processing capabilities. Spark is a open source distributed engine designed for real-time large-scale data processing. Now, it can be used for your real-time processing or also for batch processing, where the performance delivered by Spark is far better than your other processing frameworks. When we talk about Spark, Spark can access data from a variety of sources. So one thing which we need to remember here is that Spark is not having its own storage. Spark can access data from variety of sources such as SDFS, OpenStack Swift, Amazon S3, Cassandra, or an external RDBMS. Now let's look at some features of Apache Spark. So it's a real-time data pipeline. When you talk about Kafka, which is known for data ingestion when organization is interested in event processing. So data can be extracted from various online sources in real time using Spark's component, what we call as Spark streaming. If you talk about real-time processing, data can be processed in real time using Spark, and hence output is instantaneous. Thus, Spark is quite popular when it comes to near real-time processing or real-time processing, or even picking up data from a streaming source or data which is getting generated constantly. One of the other features of Spark which makes it popular is in-memory computing. Data can be computed in memory, that is in RAM, in a distributed fashion, that is across a cluster where each machine's RAM will be contributing for the processing power. So data can be processed in parallel, and this accelerates the speed of analytics or speed of processing which is being done. When it comes to flexibility, Spark allows developers to write applications in multiple languages such as Scala, Python, or Java, or even languages such as R. When it comes to fault tolerance, Spark supports and uses its building blocks that is called RDDs, which are designed to manage failure of any worker node in the cluster. And that gives a very high fault tolerance, because you could even have your computations cached, and you could also have replicas of a computed result on different node, which adds to the fault tolerance. One of the greatest feature of Apache Spark is lazy evaluation. So when you talk about lazy evaluation, that provides optimization, reduces complexity, increases speed, and saves computation. So when we talk about lazy evaluation, what we mean is any kind of computation or processing you would want to do would be lazily done only when you would be interested in result. We'll learn about that more when we talk about RDDs. Now let's look at Apache Spark architecture. Spark architecture is derived from two important abstractions. One is the building block, that is your RDDs, resilient distributed data set. That's the fundamental unit of data in Apache Spark, which is also logically split into partitions and thus can be executed on different nodes of a cluster. We'll learn more about RDDs, how these are created, what RDDs do. But one thing to remember here is when you talk about Spark, it has different APIs such as RDD. You have in later versions DataFrames and Datasets, and these are the different APIs which allow you to process the data. RDD is the building block of your Spark. When it comes to DAG, we say directed acyclic graph. Now that's the scheduling layer of Spark architecture that implements stage-oriented scheduling. What we can also understand is DAG is basically the way in which your series of steps are lined up, and Spark engine behind the scenes knows the DAG and knows what's coming in future when it comes to the execution. To learn more on DAG, you can just go to Google and type direct acyclic graph. And if you look at this, so basically this is what your direct acyclic graph is, a topological ordering of a graph where every edge goes earlier in the ordering to later in the ordering. So here we can see these arrows are nothing but edges and these circles are nothing but vertices. So that's the concept which Spark uses when it comes to processing or continuing processing with your different steps in your application. So Spark also works on master-slave architecture, and that basically consists of a driver program which basically knows the flow of your application, and this driver would run on a master node, although it could also be made to run in one of the nodes of the cluster. Now that depends on the deployment of application, which could be in a cluster mode or in a client mode. So when it is in a client mode, your driver which knows the flow of your application would run on the client machine wherever the application was launched, or you could say master node. Your driver could also be run on one of the nodes of the cluster depending on how you would want your application to run. And also there are multiple executors, which is the JVM process which will run across the worker nodes. We'll learn about this when we discuss detail about applications. Now when you talk about master node in a master slave architecture, whether Spark is working as a standalone cluster, so Spark could be installed on set of machines where you would just have Spark related configurations. You would designate one machine as master, other machines as worker, and that would be your Spark standalone cluster. You could also be having Spark integrated with Hadoop, where Hadoop's yarn would be used for processing. So in that case, you do not have Spark master and worker nodes. However, the worker nodes of a Hadoop cluster, that is your data nodes and where your node managers are running, those nodes are used for your processing. So when you talk about Spark architecture in a standalone where you have a master and slave, master node would have a driver program. Now Spark code behaves as a driver program and creates what we call as an entry point, that is your Spark context. Now that is basically the gateway to all your Spark functionalities. Normally when you bring up Spark in an interactive way such as Spark Shell or PySpark or Spark SQL, your Spark context is initialized by itself. However, if you are building an application using IDE, you will have to define and initialize the Spark context. Now the Spark context, which is an entry point, talks to the cluster manager. Now that could be Yarn, that could be Apache Mesos, or that could be just the cluster manager in terms of your Spark standalone cluster. And this cluster manager, what does this do? This is responsible for the resource allocation. So Spark applications run as independent set of processes on a cluster. So your application is broken down into tasks, and these tasks would be running across machines in what we call as executors. So the driver program and Spark context take care of your job execution. Now this is how overall it would look. So basically you have an application. Now that application would be split into multiple tasks which are to be distributed across worker nodes. Now whether it is a standalone cluster or whether it is a Spark with Yarn integrated cluster, you would still have these tasks which have to run on different machines, where each machine's RAM and CPU cores would be used for processing. Plus, not to forget that you would try to benefit from locality reference, that is the data should be existing on those worker nodes. So when an application is supposed to run, it will have various steps, and each step in the application will create an RDD. So let's say you have an application, for example, you would say X equals sc.text file. Now this is basically a text file is a method of Spark context which basically allows you to work on files, and here I would be pointing to a particular file. Now what does this step do? It does not do any evaluation. In fact, it creates an RDD, a resilient distributed data set in the memory. So at other end, if we talk about multiple machines which are going to be used for your Spark execution, here you have each machine having memory and CPU cores and obviously the disk. So say for example you are picking up a file from HDFS which is using the disk of all these machines. So what will happen with this step is X equals sc.text file. So this creates a RDD in the memory of the node. So this RDD is distributed, created in memory. This is just a logical step, but as of now the file which you are interested in is not loaded into the RDD. It is just a logical step and resilient distributed data set created in the memory, and by default this RDD RDD also has logical partitions. So we can say, for example, this RDD would have logical 2 partitions, or might be more depending on how you have written the application. Now in the next step, if I do y equals, let's take x, which is my first RDD created, and then I do a map transformation on it, what would this step do? This would not do any evaluation. This would again create one more RDD in memory, a logical step which will be executed after the first one. So here we can say there would be one more RDD created in memory, which is the child RDD, and the first RDD is the parent RDD. Now finally you could again do z, and you could say y dot, and I could be doing a filter. So that's again one more transformation which I'm doing, and this transformation will not give me result, but it will also create one more RDD. Finally, I could basically just say z dot count, where I would be interested in seeing the result. Now once I do this, this is an action. All these are transformations. This is the method of Spark context. So only when you invoke an action, the actual DAG which was created with all these steps will get executed right from the top. So this is the DAG which was created. You invoked an action which triggers the execution of the DAG right from the step where the file from the disks will be loaded into RDD. You would have a map transformation, you would have a filter transformation, which finally gives you the result. So normally when your application is run, it is split into multiple tasks that are distributed across worker nodes. Now when an RDD is created, it can be distributed across worker nodes as we see here, and worker nodes are the machines where the execution will happen. So your application has been broken down into tasks which we see here, and these tasks have to run within what we call as an executor, a JVM process. And if you would want, you can even save the computed results in cache. So if we were talking about a Spark with yarn, now yarn, as we know, would be basically requesting for containers. Container is basically a combination of RAM and CPU core. So you could say this executor process would be running within the container. Now that's how it looks when it comes to your Spark execution. That is what you mean by DAG, and that is what you see here when you talk about your different RDDs getting created. Moving further, when we talk about your Spark architecture, as I explained here, so your Spark application, that is your Spark context, is talking to cluster manager. Now cluster manager, whether that is yarn or in terms of your Spark standalone cluster, basically would be requesting resources across your worker nodes where the relevant data is stored. So what I mean here is you have an application which is interested in processing the data. The data is stored across these two worker nodes. Now, if a parallel processing has to happen, if you would want to process the data which is split and stored across these worker nodes, then you would need processing on both the nodes. If you had yarn, then what yarn would be doing is yarn's master would be requesting resources to the yarn slave, and yarn slaves would then allocate or grant permission to use the resources on every machine. In case of Spark standalone, you would have your master, which is basically making sure that each worker node has the resources which can take care of your execution. And as I explained, your application with each step of transformation would create an RDD which would be distributed across the memory of these machines. Any further transformations will just keep creating RDDs, and only when you invoke an action, the execution of your complete DAG happens. Where does the execution happen? Within the executor. So what is an executor? The JVM process where your tasks will be executed. Looking forward, executor, which is responsible for execution of these tasks, obviously needs resources, and these resources come from the worker node where the executor process is running. Now that also means that on one particular node you could have more than one executors running, taking care of more than one task. If we look further, worker nodes which are executing these tasks are basically assigned resources by the cluster manager. So basically cluster manager is requesting resources. So if we talk about something like yarn, I would have, let me explain this. So normally you would see your Spark working with yarn, and if we had a yarn architecture, as I've explained earlier, in case of yarn, you would have your resource manager, which is the master, and you have your node managers, which would run on the machine wherever data nodes are running. That's the Hadoop setup. Now, when we talk about an application which needs resources, your application contacts the cluster manager. Now, what does resource manager do? It basically asks the node manager if I could have resources for the processing. That would be something like asking, give me 1 GB RAM and give me 1 CPU core. 1 GB RAM and 1 CPU core. So this is what your cluster manager is requesting to the node manager. What does node manager do, which is keeping a track of its own resources on the machine, would basically say, fine, I would grant you access to use this amount of resources. And how does that do it? So resource node manager says, I'm fine for your application to use this amount of resources. So this request which cluster manager is making is called as a container. So it's basically a container which your master is asking to node manager. Rather than always saying 1 GB RAM and 1 CPU core, you would say container of this particular size. What is node manager doing? It approves the usage of this container. Now that's where, in terms of yarn, your resource manager starts a temporary daemon called app master. And this app master or application master is responsible for the execution. So what this application master does, it basically goes to every machine, uses this container, and basically takes care of the execution of your application related task. So it is within this container, you would then have an executor process starting, which takes care of execution of your tasks, which are dependent on the data which is coming from this particular machine. So this is what happens in terms of your Spark application integrating with Yarn. If it was not Yarn, and if it was just the Yarn's Spark standalone cluster, which has a master process and which has worker processes, it would be something similar, but you would not have the container concept. Master would still ask resources to worker nodes. Worker nodes would basically allow those resources to be used, and within those resources you would have the executor process which would be started, which will take care of execution. Now that's how your Spark architecture works. When you talk about Spark ecosystem, we can say that it has language support for multiple applications such as Java, Python, Scala, and even R. So you have different components within a Spark ecosystem. You have Spark core engine, you have Spark SQL, you have Spark streaming, you have Spark MLlib and GraphX. Each one of this is for a different use case and for processing data in a different way. So as I mentioned, your Spark can work in different ways. So it can be working as a standalone cluster, which is basically a dedicated cluster of Spark where you would have multiple machines on which you would have Spark master and workers running. You could also have Spark integrated with Apache Mesos. Now that's again a clustering technology, or you could be integrating it with a Hadoop cluster where you have Yarn as the processing layer. Now let's talk about Spark Core. So Spark Core is the engine for parallel and distributed processing of your large data sets. So basically it takes care of these things. So scheduling and monitoring jobs. So whenever you have an application which is written in Scala or Python or R, you would, or in Java, or a combination of Java and Scala. So you would have scheduling and monitoring the jobs taken care by Spark Core. The memory management, that is, your job would obviously run across nodes, and each node is contributing by its RAM and CPU core. So you have the memory management to be taken care. Also fault recovery, because we are talking about multiple machines and some of these nodes or machines might fail. So who takes care of fault tolerance? And your application being split into tasks, and those tasks to be dispatched across nodes for the processing. Now this is where the concept of RDDs comes into picture. Now as I explained just few minutes back, your RDDs are the building blocks. They are the special data structures used in Spark. They are immutable. They are partitioned collection of records that can be operated in parallel. So it supports parallel processing, and it also supports distributed processing using memory across your different nodes. Your RDDs are basically created by transformation of existing RDDs or by loading an external data set from a storage. Now there are different methods. So you have methods such as text file or whole text files or parallelize, which basically allow you to create these RDDs initially. So for example, as I said, your Spark basically has an entry point, which is your Spark context. Now that is in terms when you are using an RDD API. If you would be talking about something like DataFrames or Datasets, which basically gives you to use the Spark's component Spark SQL, so you would have in older versions such as 1.6 of Spark, you still had Spark context and you also had SQL context, which basically allows you to work with structured data. So your Spark context is made more to do with RDD API. Your SQL context is more to do with data frames and data sets, which was experimental feature in 1.6, but 2.x onwards, you basically have Spark context. And if you are working with Spark SQL, then you have something called as Spark session. So these are your classes. These are your entry point of your applications. Remember, if you are using Spark in an interactive way, then these get initialized automatically. But if you are building your Spark applications using an IDE, then you have to initialize them. Now, with your Spark context, let's look in detail. So with Spark context, you have different methods which can be used. Some of the common ones are something like text file, which basically allows you to work on a particular file, and using sc.text file is basically pointing to a file which will then create your initial RDD. You could also be working on whole text files, which is basically to work on a directory which has multiple files, whole text files. You also have something called as parallelize, which allows you to work on a collection of elements such as an array or a list or a range and so on. So this will also create an RDD. You have other things also like sequence files and so on. So these are your different methods which initially create an RDD, a resilient distributed data set which is using the memory of your worker nodes. Upon this, then you start doing some transformations, that is such as map, such as filter, might be flat map or something else. So all of these transformations will only result in an RDD. That is one more further logical step. As of now, if you see, sc.text file and then your any transformation RDD is just creating the steps in a DAG. It is just creating an RDD, but no execution is happening as of now. Only and only when you invoke an action where you would want to see the result, the execution of the DAG starts right from the beginning. Now that's how your RDDs work. Now here we are looking at the transformations, as I said. So there are mainly two operations in terms of Spark. One is your transformations and one is your actions. Remember, every time you use a method of Spark context and you do some transformations, it will only create a series of RDDs. That is a series of logical steps which will be evaluated lazily. So these transformations are operations which are performed on an RDD to create a new RDD. So you could have map or filter or join or union, and the execution of all these logical steps, execution of RDD, evaluation of these RDDs, that is loading a file, doing your map and filter and so on, that will only happen when you invoke an action. So in the end, if you would want to see a count, you would want to see the result, you would want to do a collect, you would want to filter out some lines, that's where the execution of the DAG will happen. So the two main operations are transformations and actions. Now, if you talk about Spark SQL, as I mentioned, Spark SQL is mainly to work with structured data. Now, in our real-time use case, a lot of companies have been using RDBMS, would be storing data in a structured way, and they would want to do structured processing. How do you do it? You use Spark SQL. So Spark SQL can basically work on data which is structured. Now, how does that benefit? So as I said, in your Spark backend, you have a DAG scheduler. Now, if the DAG scheduler is informed that the data is in a structured format, it would be able to process the data in a better way. So when you talk about Spark SQL, you would want to work on structured data. Now that would what we create, as we were talking about Spark Core, where every transformation was creating an RDD, here we would say it would create a data frame. Now data frame is a new word, so you could basically say it is creating a schema RDD or an RDD which has a schema embedded. So you basically have, in terms of Spark Core API, it is the RDDs, which are the building blocks. In terms of Spark SQL, you basically have data frames, or even the usage of data sets which are getting created. So this is how it would look. At the bottom layer, you have the data sources, which could be CSV, JSON, text, Parquet, or any other format. You could also have a JDBC connection with your Spark SQL to connect to an external RDBMS. Now, to work with your different data sources, internally it is using a data source API, which can then use different methods of your Spark session. So you could have, in terms of Spark SQL, what we call as Spark session. So as I said, if you are working in an interactive way, say you would bring up your Spark shell, and when you bring up your Spark shell, it has Spark context, which is initialized in case you want to work with RDD API. It also has your Spark session. And normally you would see Spark session is available as Spark. It is available as Spark. So there could be different methods of Spark. So you could be basically saying something like Spark dot read, and then you could be directly saying .json to read a JSON file. So that's one way. And then you point it to your JSON file. Or you could have spark.read.format, and you could specify what format you want to do, and then you can load the file. So whichever way you do it, you are using Spark session, which is the class, which is basically having different methods. And all of these, what will they result in? They will result in a data frame, which is nothing but a structure of rows and columns with headings. Now this is the data frame created. That is a schema RDD, which is getting created where your data is in the form of rows and columns. And then you can start using your data frame DSL or your Spark SQL queries. So you could be writing a simple SQL query like what you would do in RDBMS to process the data. And what you're doing is, when you do this, you are doing a SQL based, querying based processing, but in memory. So that's how your Spark SQL does it. So when we talk about Spark SQL, it basically has a language API. So you can work with different languages such as Python or even your Hive querying language. So you could be directly connecting your Spark SQL or Spark session to directly work with Hive, which is a data warehouse package on top of Hadoop. You could be using Scala, you could be using Java, or it could be a combination of Java and Scala. What it does, it creates a data frame, or as I said, a schema RDD. So Spark SQL works on schema, that is tables and records, and this schema RDD or data frame is basically used as a temporary table where your data is loaded, on which you can then run your SQL queries. And your data source are basically the data which is coming in from different sources. Now, if you look further, you could be using Spark SQL to import relational data from data sources, which could be in different formats such as text, JSON, CSV, Parquet files. You could be getting the data from your Hive tables. So you don't have to specially do something. You have to only have Hive configuration file within your Spark config directory. And that's how Spark will know where Hive is, where Hive's metadata is, and it can then pull out your tables or databases from Hive, and you can start working on them. You can run your SQL queries over imported data, which is either coming from RDBMS or from data sources or from Hive table, and that would then create different data frames, which allows you to further process the data. And finally, you could not only have this processed data looked at, but you can store it back into Hive tables or on SDFS or any other storage which you prefer to use. So this is how it looks with a Spark session. Applications can create data frames, and with the help of an existing RDD using a Hive table or from Spark data sources. So your data frames would be created no matter from where you get the data, but provided the data is structured. Even if the data is not structured, you can still create a data frame, but that will not make any sense. So here we are doing a read.json. We are pointing it to a JSON file, which should be existing in this particular path. Now this, if you are using Spark with Hadoop, this would expect the data to be on HDFS. if you are using Spark as a standalone, depending on your operating system, whether it is Linux or Windows, you will have to give the absolute path where the file is. Remember, if you have a standalone Spark cluster, then in that case, this file should be existing on all your nodes. Now, once your data frame is created, you can always do a df.show, and that will show you the data in the form of rows and columns. Further, your Spark session allows application to run SQL queries. That means you could always create a temporary view based on your data frame, like we created a data frame in the previous step here. And in the next step, you are creating a temporary view based on data frame. You call it people, and that's when you can start running your SQL queries as simple as this one. So you could say spark.sql and then do a select star or do a group by or do a filter. You could do all that using this. So let's talk about Spark streaming here. And when you talk about Spark streaming, it's a scalable, fault-tolerant streaming processing system, which basically supports both batch and streaming workloads. So here we would be intending to process data which is constantly getting generated, or we could say that is your data stream. And using your Spark stream, you would be breaking down your data into smaller batches of input data and then have batches of process data. So let's see how Spark streaming does that. So when you look at your Spark streaming, your data could be coming in from Kafka or Flume or say Twitter, Akka or Amazon Kinesis, or it could be coming from one of the NoSQL databases, or there might be an application which is generating constant data in a streaming fashion. Now that's the data which we would want to process, and that's where we would have Spark streaming coming in. So Spark streaming has different components, like you could be processing using Spark's RDT way. You could be processing using Spark SQL and DataFrames. So you could process the streaming data using DataFrames by interactively querying with SQL. You could also use Spark MLlib component, that is for machine learning. So you have MLlib or ML, and you could train your models with live data and then use the trained models. And finally, when the Spark streaming data is processed, you could have that data stored in, say, Hadoop's SDFS or any other NoSQL database. When you talk about Spark streaming, it basically looks like this. So this is your Spark streaming architecture. So at one end, you have your data streams, which will be processed using Spark streaming. So when we talk about Spark streaming, we would be defining a receiver. Now that's basically a part of application which will be looking at a particular socket or at a particular port for newer data which comes in. That data would be broken down into smaller batches. Now each batch is for a small interval of time. And then you have series of transformations, or basically your Spark application, which will be processing the data, giving you a final result. So you would have, if we expand this smaller box, it would look like this. So you have live input data stream. Now that data stream is divided into smaller batches, or those batches are what we call as discretized streams. Now these batches of input data are then processed through series of transformations, or you could say series of RDTs. Now, once these transformations are done, finally you can have your output. So internally what Spark is doing is Spark has its own task scheduler, it has its memory manager, which is helping you do these transformations for the constant data which is getting generated, and then you have your process data which is getting stored. So that's how Spark streaming does that. So Spark streaming has the concept of DStreams, or what we call as discretized streams. So this is nothing but your continuous stream of data, which is broken down into smaller batches. So it can be input data stream received from a source, or process data stream, which was generated by transforming an input stream. So here you have DStream, that is your stream of data broken down into smaller batches. And we can see that you might be having data coming in from time 0 to time 1. Now that's a smaller batch on which you will have series of transformations. Then this transformed data could be further handled for processing. You would have other set of data coming in for time 2 and time 3 and time 4. Now that's how Spark streaming does the processing. Now before we get into Spark MLlib, let me show you a Git link where you can find some examples. For example, if I go into my GitHub And here you can go into Scala apps, and here we have some examples for Spark MLlib, or you also have Spark application Scala files, and you can look in this, and here you can pick up, for example, this one, which is 9th app. And this is a simple example of Spark streaming application written in Scala. So here you're importing some packages, you're initializing your Spark context, right? Because you would be writing your application using an IDE. And here, then we create a Spark streaming context, which also defines the time interval for which you would want to look at the streaming data which is coming in. For this streaming context, you define a socket text stream, which tells that for this particular or on this particular IP address and port, you would be looking in for data. Then you have your series of transformations which you would want to do on that data which is constantly coming in, and then you can have it saved. So when will this application start? When we do a Spark streaming context.start, and then it will wait for you to terminate this application. So that's one thing on Spark streaming. Now Spark streaming also have an option of windowing, where basically you would not only be looking at the data which is coming in for one time interval, but might be a window based operation, that is, say, last 3 instances of the data which has come in. So the application would look something similar, but here you also have, once you have defined your streaming context, you have your socket text stream. And here I'm also giving a storage level memory only. So I would want to persist the data as it comes in memory. Then I do series of transformations, and when you're doing series of transformations, you are also using a method reduce by key and window. So that is where you would be looking at data which is coming in every 10 seconds and for an interval of 30 seconds. That's a window for 3 instances or 3 intervals. And finally, you do the processing. So you can find a lot of examples like this in GitHub. So basically, using your Spark streaming, you can be processing streaming data, which is constantly coming in, wherein your streaming component breaks it into DStreams, applies your series of transformations for different intervals, and then you have your finally processed data. Okay, now let's learn about one more important component of Spark, and that is your Spark MLlib, that is machine learning library. Now this is mainly when you would be interested in designing or developing your machine learning algorithms. So Spark MLlib is a machine learning library in Spark that is used to implement your machine learning algorithms. So you could be using one of these techniques depending on the data, depending on the problem. So you might be doing regression, you might be doing clustering or classification or collaborative filtering. So these are different techniques, right? So if you are working as a data scientist, or if you're working as a data analyst, where you would be interested in processing the data, building your machine learning algorithms, and to solve a particular kind of problem. That could be a problem which you are trying to solve, or that could be a new data-driven product which you would want to build, for which you would want to use machine learning algorithms. So you could be using Spark MLlib or Spark ML. Now Spark MLlib basically has these different features. So you have featureization when you talk about your data science, or when you talk about data science kind of activities. Machine learning is one part of it. Now, when you talk about your Spark MLlib, there are different aspects like featureization. Now, that includes your feature extraction, that includes your transformation, dimensionality reduction, and your selection. So when you talk about ML algorithms, you have algorithms for using different statistical models for different kind of problems such as classification, regression, clustering, collaborative filtering. You also have a concept of pipeline, that is when you would want to use, say, different algorithms as a part of your pipeline. Now that's for constructing, evaluating, and tuning your ML pipelines. And then you have different utilities for linear algebra, statistics, and data handling. Now let's understand about Spark MLlib data types. So when you're working with Spark MLlib, you need to understand different data types. So your MLlib supports local vectors and matrices that are stored on a single machine as well as on distributed machines. And you could have your local vectors, or you could have your label point and local matrices which can be used. So when you say local vectors and local matrices, these are your simple data models that serve as public interfaces. So there are some underlying linear algebra operations which are provided by what we call as breeze. When you talk about a training example which is used in supervised learning that is called labeled point in MLlib. So what is local vector? So a local vector has basically integer typed and zero based indices, and it also has double typed values stored on single machine. So it supports, your MLlib actually supports two types of local vectors. One is your dense and one is your sparse. So just remember that when you talk about vector, vector is also like a list, but a list which is arranged vertically, right? So when you talk about dense vector, a dense vector is backed up by a double array representing its entity values, or you can say entry values. But if you talk about a sparse vector, it is backed by two parallel arrays, that is indices and values. So for example, we can see here that you can have a vector of say values which is 1.0, 0.0 and 3.0. Now that could be represented in dense format as 1.0, 0.0 and 3.0. Or if you're doing it in a sparse vector, then it could be 3 comma, you have and then array that is of 0 comma 2 and array of 1.0 and 3.0, where 3 is the size of the vector. So you could be using these local vectors, or you could be using your label point. Now remember, when you're interested in working on these vectors, you have to import this package which is Spark, MLlib, linear algebra, and then you have vector or vectors. So that is what you want. And for label point, you would need this regression.label point package also. So what is a labeled point? It is a local vector that is associated with a label or a response. So when we talk about machine learning, in supervised learning, you basically have your features, which is nothing but some fields, and those features are then related to what we call as a response or a label, right? So when you talk about labeled point, that is a local vector. It can again be dense or sparse, and it is associated with the label response. So in MLlib, your label points are used in supervised learning algorithms. So we use a double to store a label so that we can use label points in both regression and classification. Now, if you are working on a binary classification problem, a label should be either 0 or 1. Now, for multi-class classifications, label should be a class indices starting from 0, 1, and 2, right? So a label point can be represented by the case class labeled point. And here what we are doing is we are importing the packages. Then we create a variable called val pos or POS, wherein we are saying labeled point, and then you give 1.0, and you could then give vectors which is dot dense or dot sparse. These are your MLlib data types which are used. Now you could also have, when you talk about your other data types, you have local matrix. Now that is nothing but integer typed rows and column indices. So here what we are doing is, when we create a dense matrix, we are giving in these values where we intend to create a integer type row and column matrix. Now your MLlib supports dense matrices whose entry values are stored in single double array in a column order, and sparse matrices whose non-zero entries are stored in compressed sparse column format. So we are importing the packages, and then we are creating a dense matrix where we are saying matrix.dense, and then basically we are passing in the dimension, and we are also basically creating an array which will, or passing in an array which will give the value for this matrix. Now when you talk about distributed matrix, now that's a long typed row and column indices and double typed values. So these are stored distributively in one or more RDDs. Now it's usually very important to store large and distributed matrices. So if you're converting a distributed matrix to a different format, you may need a global shuffle, which can be expensive. So there are different types of distributed matrices which have been implemented. Like you have your row matrix, which is row oriented distributed matrix. You have your, in case of your row matrix, actually it is a row oriented distributed matrix without meaningful row indices, something like a collection of feature vectors. And then it has a backed RDD of rows where each row is a local vector. So when you talk about your row matrix, it is specifically, remember, it's a row oriented distributed matrix. Now you can have a indexed row matrix also as a part of your distributed matrix that is similar to a row matrix but with meaningful row indices. You could have a coordinate matrix that is a distributed matrix backed by an RDD of its entries. And then you can also have a block matrix, which is basically again a distributed matrix backed by an RDD of matrix blocks. So you can have all of these within your distributed matrix, that is block matrix. You have your coordinate matrix, you have your indexed row matrix, and you have your row matrix. So these are the different data types which are supported by MLlib. Now let's look at a code. So here we are trying to solve a linear regression problem using Spark's MLlib. So we basically import the linear regression related package. Then we create a variable called training, which will be reading the data from a particular file. Okay, now that file is in a text format. Then what we do is we would want to create a variable called LR. Now this will depend on your linear regression algorithm because that's what we want to use. We are setting up a max iteration, we are setting up regularization parameter, and we are also setting up elastic net parameter. Now once we are done by creating or using this linear regression model, what we would want to do is, linear regression algorithm, we would want to create a model. Now, how do you create a model? You can call it some name and you will say LR, where you are using the linear regression algorithm, and then you use a fit method. Now, fit method is basically applied on your training set or your data set. Now, once you have created this model, then based on this model, you can be printing your coefficients, you can be printing your intercepts, you can get your other aspects which you would want from your linear regression solution. So you can summarize the model over the training set and print out some matrix. So here we are saying training summary, then we take our model, which is LR model, and we get a summary out of it. We might be interested in getting the total iterations. We would want to get some objective history, which we are doing here by saying training summary dot objective history. We would be interested in getting the residuals, gradients, coefficients, and intercepts. So all of this information can be printed out like this. So this is a Spark MLlib linear regression. Now you could also be using MLlib for a classification problem using naive Bayes. So in this, you are using the ML classification naive Bayes package and also a multi-class classification evaluator. So you read your file, then what you do is you create an array of training and test data set. And this is where we use a random split method, because what we would want to do is for our algorithm to be trained and then tested, we would want to split the data into 70-30 ratio. So 70% will be your training data set and 30% will be your test. Then we use the naive Bayes algorithm. So we are saying val model. We use naive Bayes because that's what we want to use for classification. And then we fit this on our training data, which would be created in the previous step. Now, once you're done with that, you would want to do some predictions. So you can use your model and you can use the transform method on the test data. So first your algorithm is trained using the training data and the algorithm which you want to use. And then we would want to try the model on the test data set and get some predictions. Now, once you have got those predictions, that's not it, right? You would also want to see how good your model is. Is it really doing good predictions? So in that case, we can be looking at our error. We can be doing some evaluation. So for that, we use a multi-class classification evaluator. We set the label column that will be based on our label column would be our label or response. Now that's where we want to evaluate if we predicting the response was good enough. We are setting up the prediction column and the metric name, that is accuracy. That's what we are interested in. And then we can print out the accuracy. So this is again a simple example of using Spark MLlib where we are still using, say, Scala and doing it. Same thing could be achieved even in Python. Now, k-means clustering. So this is again one way where you would want to solve a problem using a clustering technique. So we read the data and then we use the k-means model. So in this case, we want to set the number of k's, that is how many clusters you would want. You want to set the seed. Now that could be passed in any number. And what you do is you create a model by using this k-means and doing a fit method on your data set. Now, once you're done with that, you can basically use your predictions, or you can get your predictions using model.transform method. Once you have got your prediction, we would want to evaluate clustering. So we would use a clustering evaluator function. And here we will run it by saying evaluator.evaluate on our predictions, which we got in previous stages. And once you have that, you can print it out. So you can be using Spark MLlib for solving different kind of statistical problems, or problems where you have linear or logistic regression. When you talk about classification, it could be SVM or naive Bayes or K nearest neighbors. You could also be using decision tree. You could be solving other kind of statistical problems which could involve k-means clustering and so on. So look into Spark MLlib documentation, and you can also find more examples on running these algorithms either in Java or Scala or Python or even in R. Now, when you talk about Spark GraphX, this is basically an API built on top of Apache Spark, and it is mainly used for graphical and parallel computation. So when you say GraphX, so we have learned in past that Spark has the concept of RDDs, that is resilient distributed data sets, which are the building blocks of Spark. Now, when you work with DataFrames, then it is schema RDD, which is used. And in case of GraphX, where we would be intending to process graph-based data. So when you say graph-based data, think of data which is, say, LinkedIn has or Facebook has, when it comes to have different data points having connections between them. So GraphX introduces RDG, that is resilient distributed graph. Now, this is an abstraction of Spark RDD, and RDG associates records with what we call as vertices, or basically nodes which are connected, or data points which are connected, and edges, which are nothing but the relationship between these nodes. So if you look at vertex, it would be these data points like Amila and Adam, and the relationship is the edge between these two data points, or these two vertices. So if you look at a property graph example, now here we have different vertices or different data points like Matthew, Franklin, Norton, John, and then we have some relationship between them. So the relationship is nothing but the edge which connects these two data points or two vertices. So at one end you have a vertex table which basically has the IDs and the values and some information about them. You have the edge table which basically shows the relationship in how these two data points or these vertices are connected. So your GraphX provides different features. So it provides a uniform tool for your extraction, transformation, and load. You could also be doing the most important stage to begin with in a data science lifecycle or a big data lifecycle, that is exploratory data analysis, where you could be doing different kind of visualizations, you could be plotting in different kind of graphs. You would want to visualize your data and then see what that data can be used for. Now, GraphX also has interactive graph computations where you can be doing computations on your graph-based data. So when you look at Spark, and we have learned about these different components, so you can find a lot of use cases by just going to Google and typing in companies using Spark. Now here there is one of the case studies. So OpenTable, now that's an online restaurant reservation service which is based in San Francisco, California, and their service covers more than 30,000 restaurants in US, and they have expanded to different countries. Now, what OpenTable had was that they were facing issues while giving restaurant recommendations to the customers, and in turn also analyzing the customer reviews. They started using Spark basically to tackle the challenges or problems they had. So OpenTable uses Spark for training its recommendation algorithms. So the algorithms which would be basically recommending restaurants and the services to different customers. And for that, OpenTable uses Spark. Now they could then suggest restaurants to book. OpenTable also uses Spark for natural language processing of restaurant reviews, which can then give new topic models. So with all this, OpenTable has achieved 10 times speed enhancement. It has helped them by reducing the runtime of their machine learning algorithms from few weeks to just a few hours, and that has obviously increased their productivity. So these are your different components. You can look into the demos where we talk about Spark MLlib using Scala or Spark MLlib using Python. You can explore more on these different components such as Spark MLlib, Spark Streaming, Spark SQL and DataFrames, and also your core API or the basic building block of Spark, that is RDD. In the last video, we learned about the equation of line and how it can be represented on a graph. We also learned on using Scala and ML basically to work on a linear regression problem. And here I will give a quick demo on solving the similar problem, or in fact the same problem, using PySpark. Now here I have two machines running. So these are my machines where I have a Spark standalone cluster. And if you have a look at this, I'm also running a Hadoop cluster, although I intend to just use Spark here. So I have a Spark master and Spark worker running on this machine. And if I go on to my second machine, I have a Spark worker on this. So I have a 2-node Spark standalone cluster, which can be used to test our functionality of PySpark. Now we all know that we can always look into the Spark directory and look in the bin, which basically has the binaries. Now last time we were using Spark shell to basically run Spark and also try out ML, or also your MLlib, which are your basically the components or packages to work on machine learning problems. Now here we have PySpark and we can be using this. So let me just go back here and we can bring up PySpark. Now normally when you are trying to use PySpark, it would be using Python, which is installed on your machine. And if you check here on my machine, it shows Python 3.5.2. Now by default it would be Python 2.7, and you can do some steps so that you can set your Python to 3.5. Then you can install some modules which would be useful when you're working on a machine learning problem. So let me just show you what steps you need to do here. And what you can do is on all your worker nodes, you can just repeat these steps. Basically, first you can check what version of Python you have. Now in my case, I had in my user bin, I had 2.7, 3.5 and so on, although my Python was set to 2.7. So what I did was I did update alternatives and update alternatives to set my Python as 3.5. I checked my Python version if it was pointing to 3.5. Then I did a apt get remove Python pip if it was installed earlier. I then installed Python 3 pip, which would then be used to install say package as NumPy, which we would be using when we are working on machine learning libraries. Now, once this is done on both your nodes, you can check if both your nodes have Python 3.5.2. If you have a Spark standalone cluster, then repeat this on all the worker nodes. If you intend to use Spark with Yarn, then make sure that on every node where you would want your Spark application to run, make sure that Python is upgraded to say the latest version. In my case, I'm using 3.5, and then install your Python pip, and then you can import modules such as NumPy. Now, once all these steps are done, I can basically also show you what's in my bash RC here. And this shows that I have set my Spark path to user local Spark. Now that's where I have installed Spark, and I have also pointed it to the binaries. So technically speaking, I can give my Python commands from anywhere. Now here, I'll just do a PySpark. Now that should basically connect to Spark. And this is where we will be using PySpark to work on a linear regression problem. Now in my previous video, I explained how you express equation of a line. What do you mean by linear regression? What does it mean when you want to plot a regression line? That is basically looking into your dependent and independent variables and trying to get a regression line, that is doing a regression analysis, finding out your residuals, the points which do not lie on your regression line. Also also looking and finding out your intercepts, that is the points which lie on the graph or on the line, or you could say X or Y axis, and then also your gradients. Now, how do we solve a similar problem using PySpark? Now, obviously, we will have to import some packages for that. So first thing what we will do is we will import from your PySpark.ml.regression. I would import linear regression. Now we know that Spark has different components and it also has support of these libraries for ML, so machine learning algorithms, and these algorithms are already there. We just need to use them. So import this package. Now once that is done, then we can work on a data set. Now in my case, I'm going to use the same data set which we used when we used Scala. That's also updated in the GitHub link, which I will show you towards the end of this demo. Now here, if I look in sample files, I have various files and I would be interested in working on this e-commerce customers.csv, and we can have a look at this one. So I could basically look into this data set. This is a CSV data set which has various fields such as email, address, avatar, and we have seen the same data set when we solved linear regression problem where we use the same data set, but we did use Spark shell and we use Scala programming. Now here we intend to use PySpark and Python. So we have certain columns or certain fields here such as average session length, time on app, time on website, length of membership, and these could be considered as the features which we would be interested in. And then you have one more field called yearly amount spent, which we would then be using as a label. So this is the data set which I would be working on, and this is in a particular folder. So what I would do is I would want to create, say, a data frame out of this data set, and let's do that. So first thing is I will use this wherein I'm creating a variable called data set, and then I'm going to read in this CSV file. So let's go back to my PySpark. So I'm saying data set. Now we already know that similar way we do it in Scala. So here in PySpark, we do a spark.read.csv. We could have also done read.format, specified a format as CSV, but here I'm straight away using this file. Now remember, if you are using a Spark standalone cluster, then you would need the file to be existing on all your worker nodes. In my case, I've taken care of Python being upgraded, the modules such as NumPy being downloaded, and also this file exists on all the worker nodes. I'm also doing an infer schema to basically understand the schema of the file, and I'm using header as true, which basically means the first row of the file would be considered as header. Now let's go ahead and do this, and that creates my data set, which we can always do a show and look into what does my data set have. Now once this is done, using your PySpark, we can always do a dataset.show. Remember, it shows you only 20 rows, but then we will get an idea what we have in our data set. So you see, all my CSV fields have now been converted into a row and a column format, that is data frame, which has email, address, avatar. And as I explained earlier, these fields do not have an impact on the yearly amount spent. However, you have other fields which we are interested in, and that are average session length, time on app, time on website, length of membership. Now this is my data set already created with the respective fields which we would want to use to solve a linear regression problem. Here, as I said, we would be interested in finding out the relation between independent and dependent variables. We would look at the data, and as I said, your yearly amount spent field can be considered as label, and we already know that for supervised learning, your labels play an important role. Now let's go further, and what we will do is we'll import two other packages here. One is vectors and one is vector assembler. Now we know that when you want to work on a machine learning problem, you would have to use some feature extractors like vector assembler and also convert your data in the form of vectors. Let's copy this and basically import vectors and also import vector assembler. Now, whenever you're working on a machine learning problem, we would be using different kind of feature extractors. Now, to look into more detail about vector assembler, you can go into Spark documentation and you can click on classification and regression. You can then be looking into some examples of linear regression. What you could also be doing is you could be searching for, say, feature extractor. For example, we could go here, extracting, transforming, and then here you can search for vector assembler, which is over here, and that basically gives you an explanation if you would want to learn more about it. I explained this in the previous session. So vector assembler is a transformer that combines a list of columns. As I said, some of our columns are the features into a single vector column, and it is basically used for combining raw features and features generated by different feature transformers into a single feature vector. And machine learning would expect the data to be in the form of vector so that we can then train our machine learning models, such as, say, logistic regression, decision trees, and so on. Now, you could read more about this vector assembler and other similar feature extractors here. Let's go back to my terminal, and what I would do is I've already imported the packages. Now what we can do is, once this is done, we will create a variable called feature assembler, and here I would be using vector assembler, which would then consider these columns which I mentioned as features, and I would mention them as the input columns, and the output column could be called as output features. So basically my vector assembler would combine all these features as one column with comma separated values. So let's do that. Now once this is done, we have our feature assembler, and at any point of time you can then do a transform, or you can basically save this in a variable. So let's consider this output equals feature assembler, which we just created, and we will transform our data set based on this, and then we will have a look at our output variable. So let's do this, and then I can do a show, which should then show me that I have input independent features. Now I have all the fields as we saw in our earlier data frame, but then apart from my yearly amount spent, I also have independent features, which is basically a consolidation of values from these four fields, or four fields which have our features. Now once that is done, we can then basically create a new variable where we would want to just select the independent features and the yearly amount spent. So these are the two variables in which we would want to see the relation. So let's do this, and I have created a finalized data which is output.select, and here I have just considered these two columns, that is yearly amount spent and independent features, which is nothing but a vector of all the features. Now once this is done, we can always do a finalized data which we have created dot show. Let's do this, which shows me my finalized data which has only these two columns. So independent features is basically the set of features which have a label or a response which is yearly amount spent, which can also be used to train our data set or train our model, and also then test it against a model for making some predictions. Once this is done, let's do this, where I will say train data comma test data, where I would want to split my data into training and test data set, so that training data can be used to train your model, and then test data can be used to validate or evaluate its efficiency. So let's take this train underscore data, test underscore data. I would work on finalized data. I would do a random split into 75-25%. So let's take this one, and here we have done this. Now what we can do is then we can use our linear regression algorithm. So I'm creating a variable called regressor. I will do a linear regression. Now that needs the features column, which is our independent features, and then the label column, which is yearly amount spent. Let's take this, and then let's create this variable called regressor. Now once this is done, we can then do a fit method on our training data, which we have created in the previous step. So let's take this, where we will use the fit method, and once that is done, we can then find out our coefficients, our intercepts, and also do some predictions. So let's work on this, and I will say regressor dot coefficients, which should show me set of coefficients here. So this is my coefficients. I can also get intercepts, which is basically the points which lie on the x or y axis, and that gives me an intercept. And then I can also get the predictions. So for predictions, what I can do is I can basically create a variable called pred results, and then I can get my predictions out of it. Here I am using a evaluate method on my test data set. So I would do a pred underscore results, and then I use my regressor, which we created here. And then what we could do is we could just say regressor.evaluate test data. And once this is done, then we can pull out our predictions. So what we can do is we can go in here and we can just do a pred results predictions.show. So this gives me the prediction, and if you look at the values, these are pretty much close when you compare your yearly amount spent and the predictions what we have made based on the features. Now we can always look at more values by just adding in a value here, and we can see how close have we got with our prediction in comparison to the labels which we used. So we used the training data, and then we evaluated, or we used the evaluate method to find out the prediction when we were working on our test data set. This is a simple example of linear regression where we have used PySpark, and then either we have listed down our predictions, or we have looked at the coefficients, we have looked at the intercept, and we have worked on a comma separated value or comma separated file which has set of features, a column which explains the response or labels, and then we have been able to do the predictions on this. This is a simple example of linear regression using PySpark. For more details, you can always look at the Spark's website, and basically you can find out some more interesting examples when it comes to your linear regression or any other problems which you would want to solve. And welcome to this quick tutorial on using PySpark to work on a regression problem. Now, in my previous videos, you might have seen how we used Scala programming and we used Spark shell to basically work on a regression problem such as linear regression and logistic regression. And if you look at the previous video, I have also explained how logistic regression works, how you work on a sigmoid function, or basically if you have your data points which would then relate to your S-curve using a threshold, how would you do your predictions? Now here I have a data set in sample files, and that's called credit card. So let's look into this, and this is the data set which I would be using for the logistic regression problem. Now basically if we look into this data set, this basically has information, it has different fields. So there are 28 fields, that is V1 to V28. There is a time column, there is also amount and class, and we would be using this data set to solve a logistic regression problem. Now when we talk about logistic regression, we know that we would be interested in binary classification, which is basically resulting in yes or no, or a binary value such as 1 or 0. Now how do we work on this? Using PySpark, which is also available. So on my machine, I already have a Spark standalone cluster running, which has one master and two worker processes. Now we have used the same Spark standalone cluster to work on our linear regression problem or logistic regression problem using Spark shell. I've also shown how you can be using PySpark to solve a linear regression. And here I would give you a quick demo on using logistic regression or using your PySpark to solve a logistic regression problem. Now, for that, as I mentioned earlier, you will have to make sure that your environment is set up correctly. That is basically repeating all the steps if you have not done, which are shown here, basically to make sure that you have your Python set up correctly. Then you will have to install the Python modules. Now, if you would be working on a linear regression, you could be installing NumPy. And similarly, if you intend to work on, say, a logistic regression problem. Also, you could use pandas, which could then be used to visualize the data if you would be wanting to visualize the data and understand more about it. Now let's go ahead. Now on this machine and the other machine, I have already done install pandas and also install PySpark SQL. Now you can also have a look at this link which talks about Arrow. Now that could be used when you're working with pandas, and if you would want to transform your data frame or a Spark data frame into a Python data frame for further analysis or further visualization. So the first thing what we need to do is we need to basically start our PySpark. So what I would do here is I'll just go for PySpark. Now my Spark standalone cluster is running, and PySpark is basically the Python's way of working with Spark. So we will still have to load the data in memory so that we can create a Spark data frame out of it. And for that, this is the first step where I'm doing a read.csv. Now I already showed you a credit card CSV file which has basically transactions and so on. Although this is an anonymous file and it does not have relevance to any real data, but then this data is what I would be considering. So let's take this one and go ahead and create a data frame to begin with. Now once the data frame is created, you can do a print schema. You can look into the data to see what your data frame contains, and once this is done, you can always look into your data frame. Remember, if you are using a Spark standalone cluster, all the Python related installation has to be done on all the nodes. Your data set has to be existing on all the worker nodes. Now here we can do a df.show to see what our data frame contains. We can also do a df.print schema and basically look at the schema which shows me the different columns which are available in this particular data set. Now what do we need to do once this is done? We have already created a distributed data frame by loading the data set, and we have used PySpark for it. And what are we interested in? We are interested in finding out or classifying the transactions as fraud or not fraud. So basically we are looking for result in form of binary, that is yes or no. Now we have these columns as I showed you here, V1 to V28, and these columns are transformed features which are extracted from the main data set. So here data is anonymous and it does not have relevance to actual or real data. Now what do? We can always look at the length of the columns in my data frame. So I could do this, and we can see that there are totally 31 columns in our data frames. Now this is just a list comprehension instead of writing all the 28 columns. So we could do this, and we could be looking at some of the columns, and we could just do this to have a quick overview of what our data or what our columns containing the feature have. Now as I said, you could be optionally using pandas. That is, if you have installed pandas, you could be converting your data frame into a panda data frame. You could then visualize all your columns, how they are varying across rows, and for which we can use matplotlib. However, that is not within the scope of this session, but you can have a look. I have given you the code wherein you can import matplotlib, and then you could be using matplotlib to visualize the data in these different columns, just to get an idea of what are the spikes, what are the different variations of transactions, and if we see some kind of pattern. Now, coming to specifically logistic regression, we will have to import specific packages like what we did in Spark Shell. In the same way, we will have to import these packages over here. So let's get these packages. Let's copy this and let's have all these packages imported. So which we will need for our logistic regression code and to solve basically the problem using logistic regression. So let's get these packages. I have already documented it here so that I avoid typing while I'm giving a demo, and just import all the relevant packages such as binary classification evaluator, logistic regression, your pipeline, you have your tokenizer or hashing TF, you have your parameter grid builder, and also cross validator, which we will be using for our use case here. So let's import these packages. to begin with. And once this is done, then we can look at the columns in the data frame. We would not be interested in the first column, which talks about time. We would not be interested in the last column. So we would just be importing all these packages, and then you can just do a slicing using your df.columns, and that shows you your columns from V1 to V28. And then we would also be interested in the amount column. So classification is something we are interested in. So class is what we have left. We have left out the time, which is the first column. So we are looking at these columns. Now, what do we need to do further? So if, as I mentioned, if you would be using pandas, you could be doing visualization. We could have a visualization technique, and we would have noticed some kind of patterns or spikes. And for that, I would suggest if you are using something like a notebook, which is integrated with Spark, it will be really useful. Or you can have different ways wherein you can use matplotlib and do the visualizations of your variations. Now, we could use ROC curve instead of accuracy metrics, which to basically help us in determining and classifying a transaction as fraud or not. What we would be doing is we would be just using the column 1 onwards till the amount only, and then I would be interested in casting each column into float. So for that, you can basically get this PySpark SQL function, and let's import this. Now, once this is done, then we can basically have a function where for the column names in your data frame, we would be using a with column method, and we would like to cast it into float. So this will be useful for our further processing of the data. So let's take this for column and basically do this, and then you have to use the Python, so you have to go for indentation, and let's get this one here. And once this is done, so you would have casted your columns as float. Now once that is done, then we would be interested in renaming our columns as labels or the class. So we basically need to get the features and also the label, which is used in supervised learning. So let's take this and let's have the columns renamed. Now, once that is done, you can always look at the columns. How does it look like? So we have these columns which we are working on, and now I would be using vector assembler. Now I have explained this earlier. So vector assembler is for extracting your features, and what we would do is we would create a variable called vector assembler. Here my input columns will be all the feature columns, and they can be grouped together by calling in one column, which is features. So this is what I want to achieve using vector assembler. Now, you know, for your machine learning, it would always like the data in the form of a vector or a single vector of features, and vector is also a list, right, where your data is vertically arranged. Now, once we have used vector assembler, we can then do a transform on our data frame using your vector assembler, which we have created in the previous step. Now, once the transformation is done, then you could be just selecting the two columns. One is the features, which is nothing but a consolidation of all your 28 columns, and your label, which is nothing but the response. Now, once that is done, we can again look at what does our select show by doing this. It's a simple way of just looking what you have been doing. Might be look at particular fields and see what it shows up. Now, once this is done, then comes using our logistic regression, where we will specify how many number of iterations, what is the feature column, what is the label column. So let's create a variable called LR, and I'm using the logistic regression here, the algorithm which is already inbuilt, which Spark comes up with. Now, once this is done, we can then create a model by using the fit method on our transformed data frame. So let's take this, and we create a model by doing a fit method, which basically has to work on our transformed data set which we have created here. Now, once this is done, then we can proceed. So what we would want to do is we could be doing this where we are creating a model. We can print the model summary and we could look into area under curve, right? Now that is one option or one way of doing things. But what we would be doing is, instead of going for this one, we would be using a cross validator. Right now, cross validator comes within your tuning, so you can always look into this link which talks about ML tuning, and here it talks about how to use MLlib's tooling for tuning your ML algorithms and pipelines. So using a built-in cross validation and other tooling allows us to optimize hyperparameters, right? So one of the important tasks in machine learning is model selection, or using data to find the best model or parameters for a given task. And this is what we mean by tuning. So that could be done for individual, that is estimators, using logistic regression, or an entire pipeline which includes multiple algorithms. So you could read more about cross validator, how it works, what is cross validation, wherein you split the data into a set of folds which are used as separate training and test data sets. Now, this is what we have seen even in linear regression. So you could be using cross validator, which could be generating your training and test data set, which could then be used to test the accuracy of our problem solving or our model. Right? So read about more about cross-validation on this particular link. Now coming back here, what I would be interested is, rather than creating a model using fit method and then looking area under curve, as I said, I would be interested in going for cross-validation. So cross-validation is usually good, as we can have values fit on the complete data. Thus we can test how our evaluation metrics is working on complete data set and how good are parameters for the model. Now in this case, we need certain things. We need an intercept so that we can fit intercept for logistic or no. You need elastic net parameter, and that is basically your regularization of parameters used in ML, so that your one of the parameters does not dominate over other parameters, or you don't have any kind of overfitting. Now how do we do that? So for that we will use a parameter grid builder, and I'm saying add grid. Now here I'm giving regularization parameters. I'm then doing a fit intercept, which is being provided with both values, that is true or false, and also your net parameters. So let's take this and let's go ahead and take it to the next level. Now once this is done, we basically have to use the cross validator. So in this cross validator, we would be specifying an estimator, what we would want to use. So that's our logistic regression. We are giving the parameter map, which is param grid we built in the previous step, and we are using a binary classification evaluator. We can also specify how many number of folds we have here. So once this is done, you are basically creating a variable which is using cross validator. Now once that is done, then we can basically use cross validator to fit, or use the fit method on our transformed data frame, and we can create a model out of it. So wait for your model to be created, and then to check your accuracy metrics, we can simply do an average metrics. So this is a simple example of using logistic regression to solve a problem and to look into your data to classify it in the form of binaries, that is yes or no. And we are using PySpark to work on our problem. Similarly, you can also look at the previous videos where we have done a logistic regression using Spark shell, and we have used basically a Spark shell and Scala to solve a business use case. So let's just give it some time where it is creating this model. Now that might depend on your system performance, and you can always look at the result of this. Remember, your Spark MLlib has different algorithms already inbuilt to solve your different data science kind of problems, or basically using your different techniques to solve your different problems. So once this is done, let's come back here. And so it is just trying to use the cross validator on our transformed data set. Once this is done, the last step would be to look into your average metrics. This is done, and you can always do average metrics to see your metrics and to check your accuracy on your problem. Now, as I explained earlier, when you have your Spark running, you can always go to the UI to see more information. And here I can go into this particular link which shows me the application which was running. It's a PySpark shell. You can look at an application detail UI which will give you the DAG. It will tell you what kind of transformations happened, and basically you can click on any one of these to see what it does. You can always look at how many tasks were run, what kind of internal steps were being done in basically processing this particular data set. You can also look at the executors. You can look at other information if there was something which was cached. So we see there was something cached in memory in a deserialized format, and that was probably being used for your further processing steps. So this is a simple example of using your PySpark to use or to work on a logistic regression problem, work on your data set to classify it with binary values. Thank you.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.